Hey everybody, and welcome back to Calc 3 Online. So today I just want to do really just this one example and just kind of another problem that I can show you how we can use spherical coordinates to make a triple integral a lot easier. The reason I would think to use spherical coordinates is because of what you're integrating over. So you're integrating over this region E, which is the upper half of the sphere, okay? So pretty much anytime, there's something spherical with the bounds, it's a good idea to basically integrate over that thing. So let's see if I can draw a good upper half of a sphere. So, so that's what this is. This is 1, 1, 1 and stuff. That's what E is. And so if you see those kind of things, try to switch to spherical coordinates and it'll hopefully make the thing a lot easier. So in the bounds here, let's do, so Z from last time is rho cos phi. We saw that. And then anytime you do spherical, you're going to need that rho squared sine phi. And then let's just do d rho, d phi, d theta. And so rho is like the radius, right? And we go from like the center, the origin out here, to 1, right, on this sphere. So we're going to go for rho, it goes 0 to 1. And then phi is that angle that's coming down from the z-axis, right? So we need to come down until we get to the xy plane down here. And so that would be half of that pi angle, right? So we're going to go 0 to pi over 2 for that one. And then theta, normal polar angle, you're just going to rotate around the full 2 pi. So doing this integral out, it's not so bad for rho, which is like the first one I have set up, because basically you just have rho cubed, right? So you're going to get like rho to the 4th over 4, but we also have this 16, so I'm going to simplify that with the 4th I get. So I would get this, all right? So simplify the 16 and the 4th. Then I got to plug in 0 and 1 here, right? So I'm basically going to get just a 1, one of these, and then minus 0 of them. So, I might even, just for space reasons, I'm just going to erase this because it's, it would just be 1 eventually if I do the bounds, right? And then, this is a nice integral. You can just do u sub because like the derivative of sine is in here with cosine. So do u sub. So I'm just going to let u equals sine phi. Then d phi is, so, we'll do it this way. So du is going to be cosine phi d phi. And so now I can just basically do, sub those in, and I'm just going to have like a u du in there, right? So this is my, u integral inside there. Get u squared over 2. And then I got to go plug back in sine phi, so I get this. Okay, there we go. So, this is just doing out all the u sub stuff, plugging it in. I divided by 2 there. Plugging in pi over 2 and 0. You get 1 minus 0, basically, with the 2 there. And then the last one's, there's no, you just get it's a constant, so you just multiply by 2 pi. So the final answer would just be 2 times 2 pi, which is 4 pi. So that one really truly is like a hypervolume. It's the volume, the hypervolume of the stuff basically over this upper half of the sphere and under that object, right? And this is like a 4-dimensional surface. It's just, it doesn't make a lot of physical sense to me, but that is what we're doing here. So this is just a good example to show how kind of nice and easy a problem can be if you just use spherical. If you don't use spherical, if you think about it, you're going to basically have to do, solve this sphere for like a square root thing, you'll have to do like z equals 1 minus x squared minus y squared, all of that square rooted. And you would take the positive square root because it's the upper half, but it's going to get way messier than if you just use spherical. If you want to do it out, I suggest you kind of try and start it that way, just to like see how much worse it would be. But this is definitely much easier because it's the right coordinate system for that kind of surface.